In the exact second you hear the sharp crack of a potato chip breaking apart, over 10,000 more are being consumed worldwide. By the time you finish chewing a single bite, another huge volume of perfectly identical chips has been devoured on nearly every continent. Replicating that precise, uniform crunch billions of times a year requires stripping away all traditional notions of cooking. Culinary art plays no role here. The modern potato chip is the result of extreme agricultural engineering, precise thermodynamics, and high-speed robotics working in total synchronization. To sustain this global demand, manufacturing takes place inside multi-acre megafactories. These heavily fortified complexes swallow entire agricultural yields daily, stripping fields bare to feed the intake bays. The logistical challenge is steep. The facility must ingest millions of pounds of raw earth and dirt-covered roots, processing them continuously 24 hours a day without allowing a single soggy or burnt chip to slip through the system. Success at this scale relies entirely on a relentless automated ecosystem. The machinery is designed for one specific function: total mass production at violent velocity. The production cycle begins as 50,000 pounds of potatoes are forcefully dumped from hydraulic trucks onto the intake belts in a matter of seconds. These tubers are highly specialized. They are genetically optimized chipping potatoes, bred exclusively to carry abnormally high starch reserves while keeping sugar levels practically at zero. This visual comparison shows the immediate consequence of improper genetics. A golden chip sits beside a completely ruined one. If the sugar content in a raw potato is even slightly too high, the vegetable will violently blacken the moment it hits the boiling oil. Once cleared for production, the raw potatoes drop into an abrasive peeler. Battered against spinning, coarse-textured walls, they are violently stripped of their tough exterior skin. This diagram illustrates the centrifugal slicer. Rotational gravity forces naked potatoes outward at a dizzying RPM against stationary, razor-sharp blades. In a fraction of a second, the tuber is dismantled into uniform pieces, each exactly 53,000ths of an inch thick. The raw vegetable has survived the heavy mechanical impacts. Now, the thin slices must endure a brutal thermodynamic reaction. First, they are aggressively blasted with cold water. This high-pressure wash strips away surface starch, preventing the wet slices from fusing together into a solid brick when cooked. The slices then plunge into the continuous fryer, a 50-foot-long contained river of superheated cooking oil. This graph tracks the oil temperature. When thousands of cold slices hit the oil simultaneously, they drain thermal energy, causing a sharp temperature drop. Computer-controlled heat exchangers detect the variance and blast thermal energy back into the river, keeping the oil volatile. Under this intense, steady heat, the water content inside the potato plummets from 80% to under 2% in exactly 3 minutes. As the golden chips launch out of the fryer, they travel at a velocity that renders human eyes completely useless. To catch defects, high-speed optical cameras scan every individual chip during mid-air freefall. When an imperfection is detected, a pneumatic valve fires a microburst of compressed air, targeting the defective chip and blasting it out of the stream. The entire line maintains zero-tolerance quality control, relying on a robotic system that executes thousands of judgments every single second. The surviving chips tumble through a massive stainless steel drum, collecting a precisely calibrated microlayer of seasoning before moving to the packaging scales. When consumers open a fresh bag, they often complain about paying for empty space, what appears to be air. This diagram shows the mechanical jaws of the packaging machine. Right before the foil is sealed, a nozzle flushes the bag with pure food-grade nitrogen, displacing all the oxygen inside. This prevents the oil from going rancid. The sealed gas creates a highly pressurized pneumatic pillow, absorbing heavy external impact during transit and keeping the fragile slices intact. The empty space inside the foil is a deliberate, highly engineered defense mechanism designed to guarantee the product survives global shipping routes. The output of a single facility is staggering. In one 24-hour shift, the continuous packaging lines generate enough bags to stretch across an entire country. Despite the deafening roar of robotics, physical quality assurance remains in sterile labs behind soundproof glass. Technicians place random samples under mechanical pressure gauges to measure the exact force required to break a chip. Human tasters pull batches from the line every hour. They verify the crunch factor, the salt distribution, and exact visual hue, enforcing absolute uniformity, so a bag opened in Tokyo matches one opened in New York. Operating at this scale requires a massive drain on local resources, forcing modern megafactories to adopt strict closed-loop sustainability measures. Industrial centrifuges extract the tons of starch washed away during the peeling process to be sold off for commercial use. Advanced purification systems recycle millions of gallons of water, and the massive thermal exhaust from the fryers is actively captured to power the surrounding facility. The factory offsets its immense consumption by recycling its own physical waste and thermal energy to fuel the ongoing production cycle. Every identical bite is a triumph of mass production, a violent collision of raw agriculture and microscopic engineering, executing perfectly scaled thermodynamic reactions to turn a root vegetable into a modern industrial miracle.